Okay, so our speakers want to turn on the video. It's my pleasure. We have Catherine Potts from D-Wave. Catherine is a senior sales engineer for D-Wave. In this role, she helps identify quantum use cases for clients and supports customers with their research and application development. Her background includes building applications for quantum computing using a variety of hardware, including gate-based quantum computers, photonic systems, and D-Wave quantum annealers. Catherine earned a PhD in applied mathematics from Montana State University. On camera from SavantX, we have Ed Heinbachel. He is president and CEO. Ed has nearly 40 years of hands-on experience in the management of high-tech companies with a proven record of success in building leading-edge software products in both public and private companies. He's a technology iconoclast since the 80s, and he aspires to build teams around emerging technologies. From producing the first CD and DVD-ROM entertainment titles, he is definitely putting out there how long he's been doing this, to next-gen training simulations for 3-letter government agencies and the DoD. Ed notched a successful IPO and is now on his 3rd successful startup. Finally, our 3rd speaker will be David Osby, who is co-founder and chief science officer at SavantX. David is a prolific inventor, data scientist, and software systems designer. He's the driving force behind SavantX's advanced analytics algorithms, including a narrow AI system for enterprise search, discovery, and analysis. David has been awarded patents and has several pending patents. He's responsible for software design and data analysis methodologies and algorithms at SavantX. So with that, Catherine is going to be our first speaker. And again, everyone, welcome to our webinar.
Thanks, Susan. Hello, everyone. I'm very happy to be here giving you all a little introduction to D-Wave's products and services before we learn how SavantX leverages quantum computing in aircraft network optimization. For folks who aren't familiar with quantum computing, what it's used for, and how it's different from the computers we're used to interacting with, let me start out by saying that quantum computers are computers that use quantum mechanics in the computation process. So this is a new form of computing, and it opens up areas where other computers may have had a difficult time solving problems in the past. So much so that in some cases, we've avoided problems that have been seen as too difficult for typical classical computers to handle. Now, with the help of quantum computers, we're able to go back to those difficult problems, some of which were called unsolvable, others that we know we could do faster if we had a better tool. Here at D-Wave, we're focused on bringing that power to our customers, enabling them to reduce costs, increase revenue, and find solutions that may not have been possible in the past. Scientists and researchers have proposed many different potential applications for quantum computing systems, some of which are listed here on this slide. Now that quantum computing systems are available over the cloud, the question becomes, which type of quantum computing makes sense for those different applications? There are 2 primary approaches to quantum computing available today: quantum annealing and gate model quantum computers. Some of the proposed applications of quantum computing will be better suited for quantum annealing, and others will be better suited for gate model quantum computing. So for example, material design is expected to be better suited for gate model quantum computing, which may not be available for commercial use for a few more years. But on the other hand, applications like employee scheduling form a large-scale optimization problem, which can be tackled by D-Wave's quantum annealers available on the cloud today. Additionally, in the center here, there are some areas where the way the problem is posed could lean it towards quantum annealing or gate model systems. So for example, there are some machine learning algorithms designed specifically for gate model quantum computers and some designed for quantum annealers. In fact, on our GitHub account, D-Wave has some examples of how to use our technology in machine learning problems available for folks to check out now. One last thing to mention here D-Wave is the only quantum computing company that is actively developing both quantum annealing and gate model quantum computers, with a long history of delivering reliable quantum annealing service to clients all over the world. D-Wave is also the first quantum computing company where businesses are seeing benefit to incorporating quantum computing in their problem solving in the form of real-world commercial applications now. In logistics, pharma, and finance, we've seen customers use our quantum annealing technology over the cloud to generate applications like the ones listed here. So, for example, last mile vehicle routing, drug discovery, and even marketing campaigns worldwide. Each of these applications have an optimization problem at its core, which can be translated to be used on D-Wave systems, whether that's on the quantum annealer or using a hybrid solver, which combines that standard classical computing power with quantum computing power. Across the globe, our clients are finding tangible benefit to using D-Wave's technology through these types of applications. SavantX is one of those clients, and I'm very excited to hear more about the aircraft network optimization applications, which at its core has one of these difficult optimization problems. Next, I'd like to share a few more examples of clients that we have across the world that are seeing those sorts of measurable benefits to incorporating D-Wave's technology. First, Pattison Food Group is a grocery store chain in Canada that saw a task that was taking 25 hours to complete, reduced down to 2 minutes using D-Wave's technology. Next, CaixaBank in Spain used D-Wave's technology to reduce computation time by 90% for their hedging application. And finally, Denso in Japan developed a taxi assignment application that reduced passenger travel time by 7%, distance by 9%, and saw a 25% computation time reduction using D-Wave's technology, pointing to a reduction in the time it took to not only calculate a solution, but also they found a solution with a better business outcome using our services. D-Wave supports these applications through a comprehensive full-stack commercial quantum computing platform available today. At the very base level, we have our Advantage quantum annealers that support computation with over 5,000 qubits. Our Leap cloud service provides real-time access to send problems to our systems with greater than 99% uptime. Our Ocean software development kit provides the Python programming tools needed to develop commercial applications, as well as those examples that I talked about earlier on our GitHub account. Also, our Launch Professional Services program is available for folks who are looking for some extra help building meaningful applications for quantum systems, whether that's by identifying and formulating quantum applications, or taking some existing work to a production-ready level and everywhere in between. Also, I wanted to talk about our hybrid solvers. So along with our Advantage quantum annealer, I mentioned that D-Wave supports hybrid quantum solvers. Now, these solvers use a combination of standard computing algorithms, that classical computing I was talking about, and quantum annealing computation to solve problems. So in Leap, customers can either use our constrained quadratic model or binary quadratic model to solve large optimization problems with a hybrid solver. These model types have different benefits for commercial scale problems and are another example of the support that D-Wave offers clients as they explore using quantum computing. And with that, I'm going to hand it over to our friends at SavantX, who are going to tell us about how they use quantum computing in aircraft network optimization.
Great. Catherine, thank you so much. This is Ed Heinbuckle, and that was a good primer, especially for folks that aren't familiar with quantum computing. So thank you for that. And Susan, thank you for your kind introduction. You could have left out the part about 40 years, but I was feeling pretty young until that part. Myself and David Osby, just a quick snapshot about SavantX and what we've been up to in the field of quantum for some time now. But just to kind of gauge what we're going to do with this presentation, this is not scripted, so we're kind of into dangerous territory. And the reason we feel good with that is because that's kind of how we operate. We've lived this for so long. We're really here to share our story with you and our journey on quantum, and it's really been exciting. And I'm going to be handling the business side of it. Just a couple of slides on the business side, just set the stage, set the table, if you will, for the business case, the use case, and how we prosecuted that. And hopefully that'll be helpful to folks, especially those of you with your business hats on. For those of you that are a little more nerdy or geeky, about 5 or 6 slides in, I'll turn this over to David, and David is our chief nerd, and he'll dive in at a very understandable level of how we approach the network optimization here for our client. And I think even if you're heavy duty nerdy, you'll enjoy it. And even if you aren't, you'll enjoy it because David has a really wonderful knack of being able to explain very complex concepts in ways that even I can understand. So it'll be fun. We're going to have a Q&A at the end. Please think about questions. That's the part that we get most excited about. And we will share what we can share with you today. All right. So the story started a few years ago, and the story really was a call from an office at the Pentagon, a referral to SavantX, and the call went something like this. And it was a gentleman there by the name of James and Jordan, these two fellows, and they said, "Hey, we're in charge of an initiative to save fuel for the Air Force every year. And do you think you can help us?" And our response to which was, "We're not really sure. Tell us more about your problem and how you want to approach this." And anyway, we listened to them. We went back and forth. We actually ended up looking at their problem and the data they had available. And we thought about it. We wrote a couple of white papers just so we could get our heads around it internally, shared that. And long story short, we ended up engaging on a project with them, the first phase. But the running joke was every time we would have a discussion, they would say, "Ed, do you know how many gallons of Jet A we burn a year?" And it's like, we have no idea. So we'd play this little game, but they like to share the fact that they burn over 1 billion gallons a year. And if they could save just 1 or 2%, that would be a huge win for them. And we didn't commit. We didn't know what we could save. We thought we could save something, but we had no idea. So next slide, please. So this all codified into a mission statement. And that mission statement was to provide an innovative solution to reduce fuel consumption and therefore reduce maintenance and expand and enhance mission capabilities by optimization. So the client is the Air Force, and within the Air Force, they have a command called Air Mobility Command, and their charge is to fly material around the planet daily. And think of it as the Air Force's, DOD's, Air Force's airline. They fly roughly about half the number of aircraft that American Airlines flies. I think it's about 450 aircraft, and they fly over 5,600 flights a week. The majority of which are what they call channel flights. They're sort of scheduled lines. And then there's a lot of ad hoc, on-demand, as you could imagine, flights that occur. So interesting problem and challenge for us. So before we go to the next slide, though, just to give you a little backdrop, we've been working we've been working in the area of quantum for, 3 or 4 years now, and working with D-Wave and developing competency, developing understanding of the hardware, how to approach these problems. We made a commitment to quantum, and we made a commitment to optimization. This is actually the second, the second project that we can talk about. The first one we'd shared last year optimizing intermodal transportation, appointing trucks to cranes in a port and using the D-Wave for that. And that really reaped some wonderful benefits. And now we've taken sort of our core competencies with optimization and our hone engine. And our hone engine, think of it as this classical engine that can figure out can be applied to very complex problems and solve those problems to gain efficiencies through optimization. But key to that is, of course, quantum. And let's go to the next slide, please. So with respect to the Air Force, we needed to meet their mission, and we had to be able to move the needle, right? We had to convince ourselves first that we actually could solve their problem and that we could provide value to them in terms of increasing efficiencies. And we determined that we are able to, with the D-Wave, I'll give you the bottom line up front, with the D-Wave and applying our algorithms and our approach, we're able to save significant amounts of fuel. We'll talk about actual numbers at the end here, but it actually ended up being a very interesting range based on constraints. And we're able to maximize the throughput. And by doing so, you minimize the number of aircraft required to meet the mission, to move the material, the cargo. And by using less aircraft, you reduce maintenance, right? And this, we looked at it classically. Can we solve this classically? Can we run HPC against it? High performance computing, clusters, and can we do it in a timely fashion? And the answer was no. You really needed quantum to do this, because the periodicity in which they need to look at the network and make changes to the network is measured in minutes, not months. They really needed that capability. So, and through this, we actually ended up, we engaged for a phase 1, and we completed that phase 1 really substantially in 6 months. And we briefed it up to the client, working directly with Air Force Research Labs. They're the pointy end of the spear, and working with AMC. Of course, we work with the AMC people, Air Mobility Command. And it's great because AFRL, they're a bunch of bright people. They're really fun to engage with. And going through this, we have a background in working with other facets of the Air Force, and we realized that, wow, given what we're doing with network optimization, there's another facet of this nobody asked for, but we sort of thought through this. Wouldn't this be cool if you have an Air Force base, as an example, and there's a hurricane quickly approaching, and you need to disperse the aircraft right before the hurricane hits. So where do you send those aircraft? Well, for the most part, that's handled by sort of like, oh, let's go, hey guys, let's go to Las Vegas. Let's move the birds there. Whatever's easy and perhaps attractive. But with Hone, with network optimization, utilizing the D-Wave, we're actually able to intelligently position the aircraft, knowing the patterns that in the past. So if we can dispatch birds to certain air bases, knowing that once the threat passes, they can actually move back into the network and the flow in an intelligent fashion. And that's huge. Next slide, please. There's so many places to go on this. I get excited. So just kind of go walk through how we approach this from a business standpoint. Obviously, we are results driven. This is not research projects for us. We are only interested in solving real world problems, and we're interested in approaching these problems in such a way that we minimize the risk for us and our clients right from the get-go. And we do that by rolling to a digital twin, and we'll show you an example of this. But this process is, we get the client data. David will talk more about this. We do a lot of data science. We test many quantum approaches in this sort of safe space of digital twins and our tool sets. We refine the model, and then we move forward with that. Next slide, please. So here's the point at which you don't have to listen to me much longer. We're running it's a short little 3-minute capture of actually running Hone, doing network optimization on the Air Mobility Command network. So we took 15 years of data, and we went through a bunch of processes, and then we built algorithms to run on the D-Wave to optimize this network. And David will take that a bit further there. Apologize that it's kind of small, but it looks a little bit like war games right now, but those are not ICBMs. Those are actually flights, and the green flights are flights that would normally occur, and then the more of the yellowish arcs are flights that our system commands they should go fly, because it's more efficient to fly these other flights. And through this, it's and we'll get into the numbers, kind of say that more towards the end, but it was quite fascinating of the efficiencies that we're able to gain utilizing the D-Wave and our approach, our algorithms. So David, I'm going to turn it over to you and let you get into more of the down and dirty on this, but thank you.
Yeah, so let's look at this panel here before we leave this slide. On the left, you'll see a classical score and an optimized score using quantum. And you'll see quite a difference in the numbers there. We'll talk more about that as we get into it. So let's go on to the next slide, Catherine. Okay, first of all, if you're a practitioner in this space, you've got to have data, right? So we have a couple of rules. You can't have it too soon, and you can't have too much of it. And usually with clients, it can be a little challenging for them to get their data together. It can be siloed. It can be in a place that's kind of inaccessible. But in the case of the Air Force, we were lucky. They were able to come up with the data kind of right away. And then the next thing you have to do, and I'm sure all your data scientists out there can relate to this, is janitorial. You've got to clean up the data, and we actually laugh a bit, but it's actually kind of true that about 95% of your effort will be spent on janitorial, typically. And the Air Force is no different. They had data sets, airplanes would disappear for a while, like where do they go? And they would say things like, well, we can't tell you that. So, so we ended up building after choosing our time period, we built a synthetic data set to make sure that the data that we were simulating didn't have any gaps in it. And that we wanted to make sure that the data that we had could support the project. And it has to also support the digital twin that we anticipate making. Sometimes the data is just plain wrong, like at the port, their inventory wasn't actually that accurate. And obviously that can affect the quality of the digital twin. But those are all things you have to consider at this stage of the game. So next slide, please. The next thing we have to do, maybe we know this ahead of time, which are to figure out what the key performance indicators will be. Usually the client knows, like in this case, they just wanted to burn less gas. But actually, we didn't actually end up with that KPI at the end of this project. We ended up with something related to it, which is what they call a short ton miles per gallon. And that basically is a measure of how much stuff you can move for how much fuel. And it turns out that they already know this at AFRL. They know that if you reduce the short ton mileage per gallon, then you also burn less gas. So sometimes, though, you have to go to subject matter experts to help with the KPIs. Sometimes the data will indicate how you can extract KPIs that are of interest. And then later you might, in your simulation work, you might actually figure out KPIs that are of interest, kind of the low-hanging fruit, as we call it. Once you determine the KPIs, then you have to really figure out whether the data set can actually support the investigation of those KPIs. And then, of course, everybody's interested in, what was the KPI before you started the project, and then what is it afterwards. So next slide, please. In the case of the Air Force, this was a rather different problem than the one we solved at the port. Still a logistics kind of problem, but you start thinking about, can we apply traveling salesman algorithm to this? That's not going to work in this case. There's another algorithm called max flow, which is actually the one closest to what we ended up doing. And then you have your greedy classical algorithms. And there's a bunch of new ones on the horizon, which we haven't investigated very much. They're often classical and haven't been turned into quantum algorithms yet. Or you might even come up with a hybrid, which is sort of what we did. And to Catherine's point earlier, you have to consider the hardware that you have to work with. Do you have a supercomputer hanging around? Most people don't. Do you have, a nice set of servers in a server room somewhere? That could help. Should you maybe use a gated computer? And also, to Catherine's point, you have to kind of think about your problem and decide what the best solution is. And then, of course, we have the D-Wave and the annealers. The truth of the matter is that really only the annealers seem to be up to these kinds of tasks that we're going to be talking about here today. So let's go on to the next slide. This is just a little bit of pretty artwork, actually. But anyway, we're going to be talking about graph theory. And that's kind of like the weapon of choice for this kind of work. I'm sure all of you are familiar with it. This just to show the idea of how complex these networks can get and that they have this feature called clustering. So let's go on to the next slide. So we're going to get into the clustering part in a moment, but in the meantime, we're going to talk about MaxFlow because, obviously we're not going to tell you how we did the project for the Air Force here today, but we will tell you about some of the things that we traveled through on the way. So MaxFlow is an interesting algorithm. You basically have a source of stuff. It could be electricity, it could be water, it could be fluid, it could be cargo. And then you have a sink, which is where that stuff's going to. So you can lay those out into a bigger graph, which you see on the right there. In this case, those nodes in this graph are actually abbreviations for air bases. And by the way, all this data is totally synthetic. So, anybody wants to try to figure out what the Air Force is actually doing, good luck. This won't show it to you. But anyway, you have these flows. Now on the right-hand graph, you can see that I can't, I guess maybe Catherine can point at AS flows down to HDY, and JZ flows that same direction. And so MaxFlow is good at this. And you have the sources and the sinks. And in the case of the Air Force, they actually have a lot of that kind of activity with their cargo, namely material moves basically from sources to sinks. That's not true of commercial cargo as much. Hopefully, the country that's receiving this stuff has a balance of trade and they can send stuff back somehow. But in any case, in the case of war, the business of war, it's often just one direction. So it would be tempting to think that MaxFlow could work pretty well. Okay, next slide. But there's a few problems we'll get into in a minute. First of all, you want to look at along those routes going from sources to sinks. Like on the left-hand graph, you see just a single thing on the edge there, which I'd call W, or weights. That's like the mass of the cargo being sent. And those are labeled on the edges. And on the right-hand side, we see you can have actually several things on an edge. And again, things typically are flowing from the top left to the bottom right. Okay, next slide. But in the case of the Air Force, they have a few glitches, right? To being a straightforward MaxFlow. They have things like training missions. And you notice that one airbase there in the center, you'll see something leaves and comes right back to that same airbase, so training missions. And then they also have to get the aircraft back to the beginning. Now, electricity, you don't have to worry about that so much, right? It flows in one direction. Not exactly true, but for the purpose of MaxFlow, it does. In the case of the Air Force, they have to get their aircraft back from wherever they end up, back to the beginning. Return to home. Next slide. So this might be a better representation of a piece of the global network for the Air Force. You can see many air bases on here, and you can see that each of the edges has three different components: distance, weight, and volume. And so now this is the thing they want to optimize, and they would like to do it in a fairly reasonable amount of time. And that turns out to be an NP-hard problem if these graphs get very big. So let's go on to the next slide. So what we ended up doing for the Air Force is we took their global network, sort of represented by the graph on the left, although it's actually much bigger than this. And then we want to break it into computable chunks, which are on the right. And believe it or not, that graph on the left is exactly equal to the 3 graphs on the right. And you'll notice that all the same error bases are represented, although graph number 1 and graph number 2 only have those error bases in common that are in red. Okay, and graph number 3 is a graph we love to find, which is a connection, kind of a global network connection between the subgraphs. So if we can compute, say, graph number 1, if we can optimize that, if that's the limit of our computational ability, then, and if we do number 2, and then by combining all the remainders of number 3 between all the different partitions we make, we can then optimize the whole network. Okay, let's go on to the next graph. This is just an example of, actually it's a repeat of partition number 1 from the previous slide. You can see the 3, or actually there's 4 error bases there in red, and then the blue are the unique ones to partition 1. And the next slide will show the partition number 2, and you can see some of the same error bases in red there. And then partition number 3 is nice and simple. And when we combine all the number 3s that we end up by doing all the partitions on the bigger network, then we end up with a kind of a global network. What happens, in fact, is that the Air Force typically flies a lot of stuff to several like distribution points, and then they go out from there. So let's go on to the next slide then. So we put this all together. We do it in the following fashion. Move basically from the left-hand side of the flowchart to the right side. We acquire the data, we've talked about that. We agree upon the KPIs. And then we found that we can trifurcate the effort into 3 branches, which is helpful because we have actually people that specialize in these different branches. The top one is a building of the digital twin, and we might do that either as a what we call a mathematical sim, which is like very low quality graphics, but it's actually accurate mathematically. Or it might be a higher quality sim, like the one you saw, where we might use an Unreal 3 engine, 3D engine. So those are more expensive to make, but sometimes it's a good thing for the client to see their data in that fashion. So we have a team that does that. Then we have another team that data scientists that analyze the data. And then we have another group that might be involved in looking at actually the algorithms required. In this case, it was partitioning the network. So those can kind of happen simultaneously. The boxes in gray are where we use the D-Wave to help us. Obviously, it ends up being in the final result operationally, but it's used quite a bit in the research side on these 2 different branches anyway. So anyway, we end up with this big box at the end there, where we are using the digital twin to explore different possible ways of optimizing the network. So it's like I guess you call it incremental development effort. And we may make many, many loops through this. I think in the case of the Air Force, it was a number like 20 major loops through it. And that's the basic flow that we follow. And I think that's the end of my slides, right, Catherine? Do I have one more? Oh, I think Ed's going to talk about this one.
Yeah, well, we can kind of tag team here, David. Thank you. Maybe, David, can you share in terms of the, let's see, as we're going through this process and as we're refining the algos, can you give the audience a little taste of what that looks like in terms of hitting the D-Wave sort of the veracity of that?
Sure, and that's a good point. The D-Wave is great. It's a great service, and it's really unmatched out there. We've looked around quite a bit. We thought about gated versus annealing. We've experimented with that, but the truth is, nobody comes close to matching the serviceability of the annealers. At the port, we had to call the D-Wave. We had 10 rows of piles of cargo, and we had up to 30 to 50 trucks in a line, and we had to figure out which truck to call up. And so it turns out we were on a 2-minute cycle. So for each row, so there's like every 12 seconds we were calling the D-Wave. And it was very successful at doing that. And that was a critical piece of the total solution there. In the case of the Air Mobility Command, it's a little different, similar but different. They want to be able to push a button and re-optimize their network. And we may make, during that optimization effort, like 100 calls to the D-Wave. So obviously, you don't want to be spending an hour for each one of those calls. Or in some cases, like with the gated machines, you can wait for days. I don't know if you found that, Catherine, but we certainly have seen that. So we've got it down to where we can optimize the AMC network in about 30 minutes, which is well within what they would like to do.
Yeah, that's great, David. Thanks.
Mhm.
Just to kind of recap. So what we're sharing with you is the results of a phase 1 on this project, where we had a mission, we had KPIs established. We launched into the project. We did all the data, the janitorial. We got the data. We did the janitorial side of it. We did all the heavy duty data science. We wrapped that into our Hone engine, optimizing it for network optimization on the D-Wave, and we came up with results. And those results compelled the client to move to the second phase, which we're in right now. And that second phase is to further refine the algos and also look at bringing in some other factors. We didn't talk about load mastering, volumetric efficiencies of the cargo. From that perspective, we're not even looking at that. There are huge areas of opportunity that will also be expanding this to that obviously quantum is the perfect tool to apply this against. And so on the phase 2 right now, we're creating an API, and then we're working with the Air Force. They've contracted with a new vendor that they plan to integrate into AMC. AMC is, as you probably could think about this, it's been around for a while. So any organization that's been around for a while will have a lot of legacy systems, and they're no different. And to the Air Force's credit, they want to upgrade these systems, and they see us as an important part of that process. So to take, if you will, a new, more modern scheduling system, but power it with the D-Wave through our Hone system, and be able to do this massive network optimization across the entire globe within 30 minutes at a punch is pretty amazing. So that's where we're on right now. We're on the second phase, and working on further optimization and being able to provide an API to them to put this into practice. So what we're describing today, just so we're clear, is we have taken the data, we have done the digital twin, we have proven to ourselves and others that this is the right path. This is the path of righteousness here and of goodness. So we're very excited about that. So let's get to the fuel burn thing. So kind of saving that to the end here, but we had a little bit of a problem. So when we're getting the numbers back. And again, as David said, the digital twin we showed you, the output of which is a nice, pretty, representation of the globe when you can move around and you can see all the flights, and we can accelerate time and do all this sort of stuff. And we used Unreal Engine 5 to do that with a different team, and that's really cool. But so we do all this, and we end up with we ended up getting these numbers out, and we're like, oh my gosh, no one's going to believe us. And we checked and we double checked and we triple checked. And we're getting through the digital twin, using their data and the process we described here, we're seeing anywhere in the low 30s to 42% increase in efficiency. And so we looked at, so the team, we looked at each other and go, no one's going to believe us. Well, we went ahead and we briefed this up to the client, to the Pentagon and to AFRL, and we said, you guys aren't going to believe this, but here's the numbers, here's the data. And they're like, oh, we believe you, but no one's going to believe us. So we ended up basically all agreeing that let's call it 8%, which would be huge. And we know it's an extremely conservative take on what we're able to achieve. So that was kind of a fun little story in there. And then through this, because of that, having less aircraft flying to move the same or more cargo, you actually reduce the maintenance, right? And we're seeing a 15% reduction in the aircraft needed, and thus less maintenance, of course, if you're not flying them. And then the quantum break glass scenario actually is very intriguing from the Air Force's perspective. They haven't thought about that, and that's an important piece of this deliverable going forward is to bake that into the API as well. So it's been a fun journey. We're in the middle of it, and we're moving to that point where we're doing the it's not a technology risk, it's an execution, just executing on creating the API, refining the approach, creating the API, and then doing that integration into an operational system. That's where we're going next. So it's very exciting. And we're really thankful for the Air Force having faith in, putting some faith in us to tackle this, and for D-Wave to work with us on this. And it's been a lot of fun. And of course, we see all sorts of applications on optimization here. So I think that we've covered everything on our end, and we've got, I think we're pretty close on our time here.
If I could make one more comment about
sure.
that.
Yeah.
I think it's kind of important. So we weren't actually tasked with doing the break glass, as you may remember, Ed. But once we realized that we could actually re-optimize the whole network in 30 minutes, it brings up a whole new way for them to actually do planning that they've never had before. Before they would do these channels, which were like memorialized thing. Well, we always send stuff from here to there, and we send so much of it, and we kind of know we're doing it. And so they built these channels, and makes it intellectually easier for them to plan. But now, when they saw the break glass, I think they're thinking, oh, you mean we could actually optimize our whole network every day? And you can. And then the idea of channels completely goes away. So can the client actually pull this off? Will their culture that they have allow this to happen? And if they do, then they could gain efficiencies, in above 2 digits. Let's put it that way. So yeah. I think that's the big thing. We hit this kind of issue at the port too, is that even although we could come up with a solution, can you get the people on the ground to actually implement?
Yeah. David, thanks for mentioning that. That's a really good point. And I think that for those of you in the audience who are thinking about, some, not just evolutionary, but revolutionary application of quantum technology to your problem sets, you can do this stuff, right? These are all, it's amazing what you can do with it. But to David's point, if you build it, they may not always come to use it. You'll have to work the cultural side of it. So that's really important consideration as you're going through this process. In fact, I would even suggest you sort of dual track that and plan. But anyway, so I think we're right on time here. So back over, Catherine and Susan, over to you.
Great. Thank you so much. That was really interesting. We've got lots of questions that came in. Catherine, if you just want to go to the next slide for a second. We are going to send out the slides. So while you may not be able to click on these links right here, in terms of kind of learning about quantum, how you get started, how you actually do quantum programming, lots of resources. So next week we will send out an email both with a link to this recording as well as to the slides. So let's get right to it. We've had some great questions come in. The first one, is there any significant differences you can share between the port cargo project and the aircraft network optimization project from a business perspective?
Oh, I thought that was going to be a David question, and then you
Me
get a
too,
singer
Nick.
at the end there for me.
Yeah.
From a business perspective, yeah, it's different. It's different in that, one is you're working with private industry and you're able to, as a port example, and you're able to approach the problem set and you're able to approach it with different business models. And those business models are cool because what we like to do in, we'll say, the non-government space in private and industry is we like to be incentivized. And so if someone's saving $100 million a year, literally because of a system that we have produced for them, to use that number, let's be a little more, well, I'll say 100 million a year, just to have a round number. We like to be able to, we want to be incentivized. And so we like to share some of the risk up front and then have a little bit of the back end. So those are kind of fun models to work with. And most companies who recognize that if you're making this a much bigger pie for everybody, they're more than happy to give you a little piece of that pie. I always like to use the food analogies. And then the other part of it is on the government side, they're not configured and can readily comport themselves to do sort of those incentives. So from a business standpoint, it's a little bit more, it's a narrower lane you have to operate in. But I would have to add to this that the Air Force is working with a group called now the Defense Innovation Unit, and they're very much forward thinkers. They're out of Silicon Valley, and they're looking to bake in some really good business practices and incentives into the model. So we enjoy some of that new thinking within the government. So that's changing in a very positive way.
Okay, well, we have a lot of questions for David, so I will just shoot some of those out.
Oh, good.
First question, is it always possible to partition the graph in an exact way, or are there approximations adopted?
Well, yeah, that's the real problem, right? Those are difficult issues. The first year, the phase one, we actually manually partitioned the graph, and then we optimized each of the pieces. And the reason why we could get away with that was because it turns out the Air Force operates in like these regional areas, and they're called areas of operation, and they tend to stick. The flights tend to stick within those regions. So we were able to manually divide up the problem that way. And then then the D-Wave we use for the optimization of the pieces. So there's two things, right? There's the partition of the big graph into smaller graphs, and then there's the optimization of each of the smaller pieces. On phase two, we're using I guess you call it a hybrid between a manual operation and a classical operation and a quantum operation to do the partition. We've been working a lot with MaxCut, which is a way to partition a graph. And as long as we stay within certain limitations of the D-Wave, we can use the quantum piece for that. So, yes.
Okay. Was the graph partition algorithm developed by SavantX, or was it based on state-of-art published algorithms? And part two of that, what was the size scale of these graphs? Hundreds, thousands of nodes?
Okay, so we found that we could get good optimizations from the D-Wave with about 50 nodes, because the nodes are fairly interconnected. If you go above that, you're starting to challenge the hardware capabilities. Classically, you can't really do that. Actually, there's an interesting story where at first we thought, we're just going to optimize this network using GAN, which is an adversarial network, AI. And we started down that path, and we learned that the GAN was going to take like a month to finish one optimization cycle. And so we said, we can't even get a couple cycles, right, in the time period we have for the project. And so we had a parallel effort to use the D-Wave, and turns out in one night before an important demo, the guys came up with a way to do it in the D-Wave. And it did have to really consider the limitations of the D-Wave, partition the graphs so that they're small enough to run the D-Wave. That is the trick. If you can do that, it will work. If you can't do that, then you're out of luck.
Okay, can you say a bit more about the internals of the algorithms? Did you map the algorithms to QUBO algorithms?
We typically go direct to QUBO. We don't actually use the hybrid solvers provided by D-Wave. And the reason for that is, first of all, we have people that have been running stuff on the D-Wave hardware for many, many years. Some of our people come from the lab up here in Los Alamos nearby, and they had an early D-Wave, and they've had one for quite a while. So they know a lot about the hardware. So we were able to stay within the constraints of the hardware and through their knowledge. And we also found that any given algorithm out there isn't quite right for what we have to do. So we always end up having to modify it anyway. So I guess you could say we're building a set of tools that allow us to do these things on our feet in a rapid fashion. We do read a lot of papers and we do gain a lot of insights and ideas from those. But at the end of the day, we end up custom coding it.
Okay. Do you deal with crew management as part of the route management? And how does this process differ from airline scheduling systems?
Mm-hmm. That's a really, really good question. And we actually had a prior Air Force project called Rhythm, where we were involved in crew, basically determining whether a crew was certified to fly. And that's a very complicated problem all unto itself, it turns out. We did not consider that as a constraint in this project, at least at this point. We were told by the powers that be on their side, on the client side, that they have that covered. I think it's partly because they have a captive audience of pilots and they can just basically tell them to, take that airplane and fly that there, and then camp, under a tent under the wing if you have to, I guess. Anyway, we didn't have to worry about that. And actually, thank goodness that, and we did not do the load mastering, which is another complex part of the problem. Each of these are pieces that would be susceptible to quantum computing, though, for sure.
All right, a question for Ed. You noted that you estimated 30 to 40% savings, but had to publicly state much lower to avoid disbelief. Do you still find this skepticism prevalent?
No, hasn't been an issue in terms of our comms with folks within the Air Force, the Pentagon, AFRL. No, I think because we've been able to demonstrate the technology in use, and we have the data to support this, so it's very compelling.
And
also, we have one other thing is that we have another thing we did not do in the phase one was optimize the global network. We can always say, well, we could, that number could fall from 40% down to 2% in theory. We don't think it will, but it could.
Another question for Ed. How do you work the cultural side? Let the customer be risk averse, shorter flight paths, not build a maze. How do you establish confidence and credibility with quote unquote weird new tech?
Yeah, it's a good question. I'll give you just a real short little example. We have a technology we call Seeker that we built, and we've been modifying, and recently we brought it into the world of Gen AI. But through its iterations, we deployed it at commercial nuclear power plants, and it's basically at that point it was a search and discovery tool across 100 million documents. Some of the documents 50,000 pages in length. And so here's this wonderful new tool that would actually learn the vocabulary of a nuclear power plant. So it would learn about 500,000 unique terms, part numbers, et cetera. This wonderful tool for engineers, right? So the first thing we did, first on the pilot, we deployed it during what they call an outage, and into a group called the EFIN, the Engineer Fix It Now team. It's basically the engineer SWAT team while they're in outage. Because for every minute a nuclear plant's not running, it's costing them about $250,000, most plants, in terms of lost revenue. So they want to get the plant refueled and get everything repaired and get it up and rolling quickly. So we set up the system and no one wanted to use it. And we're like, damn. So what I did is I literally would go into the EFIN team offices, and I would bring boxes of donuts. And on the donuts, I scrawled, one search equals one donut. So nobody got a donut until they went and used the tool. And I did that for about 3 days. And then I didn't need to bring any more donuts. So donuts can work miracles.
That's a great story, Ed. We just have time for a couple more questions. I'll run through them. One for David. How many logical qubits do you typically need to represent your optimization problems?
Well, we need to stay within the hardware capabilities. They're increasing all the time, but like I said, it's around 40 to 50 fully connected. And then on the D-Wave, of course, your QUBOs have to chain them and things like that. So yeah, I would say that's a good number.
Okay. I'm not quite sure who this goes to, Catherine or David. Is there any utilization of multi-factor design optimization within the realm of quantum computing?
That's a Catherine question, I think.
Well, I'd be happy to talk about that one-on-one. So please shoot me a message, whoever asked that question. We see lots of different applications in all different sorts of areas. So there's a lot of material out there. I'm sure I can find something that you're interested in, for sure.
Okay. And another one for Catherine while we have you. I have a Python code using an old version of the Ocean API. Some of the functions are deprecated. If I want to run it on the latest D-Wave machine, do I need to migrate the code to the latest version of the API? Or is there a way to run an old version of the API on the latest D-Wave machine?
So I know that the best way to do it will be to migrate the code. Then you get the most up-to-date resources available in the Ocean package. If you're having difficulty doing that, on our LEAP page, the LEAP UI dashboard page, which everyone who has an account on the D-Wave system can access to, there's a large amount of community posts. You can certainly check those out, or you can reach out to our support line, and we're happy to help you out.
Okay, and with that, I think we're done. We didn't get to all the questions, so we will try and answer them over email. Again, thank you so much to our SavantX team for all this the great work and the great presentations today. And thank you, Catherine. And everyone should expect an email from us with a follow-up with links to the slides and to the recording. We will have another webinar next month, so you'll get information about that soon. And again, thank you all for your time today. We really appreciate you coming.
Thanks,
Bye-bye.
everyone. Thank you.
Thank you.
Thank you.